外在把产业，也做台湾在。
My name is Qi from 东华大学。
My name is Li from 中正 University.
from National Taiwan University.
Introduce your team by Typt, first from reporter.
Honorable juries and our competitor and leader of Team Excelsior Holdingship. Anchors my teammate Zhao Mingxiang, Chen Liangyi, Wu Hanxue, Wu Yizhen. Thank you.
Hello everyone, we are Team Epsilon from Kaohsiung Senior High School. I'm leader Xu Yizhen, Wang Lingxuan, Li Haozhe, Chou Yuden, Jie Haorun.
Hello everyone, we are Team Review from National Senior High School. And my name is Fan Haoyuan. This is Zhu Longxuan, Huang Qirui, Liu, and Xiao Yu.
Hi, thank you. Why you want to try? 13. So, reporter accept or reject.
We regret.
Reject.
Regret.
Reject.
Okay, who would like to challenge 26?
6. Reject or accept.
We accept.
Accept. Please write down your name on the form. Five minutes for reporter to prepare.
Number 3 is the of the competitor and the reporter from Excelsior. And today what I'm going to report is problem number 6, magnetic mechanical oscillator. And here's the problem statement. Secure the lower ends of 2 identical lip springs to a non-magnetic base and attach magnet to the upper end such that they repel and are free to move. In this case, how the movement of the spring and depend on the regular parameter. And the reporter will mainly focus on why the spring will have coupling motion, and how the oscillating frequency change in different parameters, and what kinds of conditions make the coupling most significant. And here's my outline. First is preliminary, including the set of 3 stages of coupling condition. That's the definition in our report. And next is the explanation of the phenomenon, including the quantitative explanation, Euler-Bernoulli beams, Lagrange equation, and adding the air drag into the equation of motion. And next is the measurement and the analysis, including the constant measuring, distance, length, and the magnetic force. And finally, the conclusion. And here's the preliminary. And here's our setup. You can see that it has a lip spring and the magnet. And it's situated in a different table to avoid the resonance between 2 lip springs. And the device used to release it, we use distance reader and the servo motor. And here's the observation video. You can see there has some significant coupling situation. And for the stage 1, which is non-coupling, when the distance is long enough, when we check the lip spring, the graph will be like this. So where there are no obvious beats, which we define as a non-coupling, and it has a passive side and driving side. And the stage 2 for low frequent coupling, you can see that there has some beats in the graph. So when one of them rises up, the other drops. We define as a beat. So when there are 6 to 15 beats peak in one beat, we define it as an obvious coupling. In the stage 3, we define it as a high frequent coupling. So when there are fewer than 5 peaks in one beat, which means that it has non-obvious coupling like this graph shows, as the distance changes. So the repulsive force of the magnet at the equilibrium point are 0, like if the position is -1 cm. And here's the explanation. For the quantitative explanation, you can see that the repel force drives the passive side to move, like this animation shows. And the passive side oscillating due to the spring natural frequency. And while the M2 of the passive side increases, it is turning to decrease the M2 of the driving side. And it will do it again. And when the distance becomes larger, it takes a longer time to increase the M2 to the same level. And while the M2 of the passive side suddenly gets large enough, it can affect the motion of driving side. Thus, the period of beats increase when the distance increases. And here's the theory about the Euler-Bernoulli beams. First, we calculate the kinetic energy of the beam. We can know the deflection and the relation between the force and the moment of inertia and the Young's modulus. And by derivation, we can get the total kinetic energy of when the Bernoulli beam is vibration. And next, we calculate the potential energy. We integrate from 0 to the deflection, and get the potential energy will equal to this. And by using Lagrange equation, we can know the Lagrange equation is by kinetic energy minus the potential energy, which including the kinetic energy of the magnets and the kinetic energy of the lip spring and the potential energy of the lip spring and the magnetic potential energy. So by solving the equation, we can get the double theta 1, double dot theta 1, and double dot theta 2. So when adding the air drag, and we can get the torque caused by the air drag. So when we're adding a drag, the equation will look like this. So this is our numerical solution. You can see that our theory perfectly predicts the phenomenon. And here is some deviation. It's come from the setup. And by measuring an analysis part, first we measure the Young's modulus by using a vertical force loaded on the center of the lip spring. And by the equation of the deflect curve, we can get the K, which is the elastic constant of the phenomenon. And next is all the about the measurement of damping, and we can get the air jet coefficient will be look like this. And first experiment is that we do a distance between different lip spring, and this is the distance. So when we analyze the graph, you can see that there has some coupling situation, and this also fit the theory. So the equilibrium angle is not at the zero, it's due to the magnet will repel. And because the period of the big change while the distance get different. So for fast Fourier transform, we can get these two different graphs. So two obviously can be observed after doing a fast Fourier transform, while the distance increases, the omega-1 tend to decrease more significantly compared to omega-2. So here's we pick out every peak to analyze. Since that the period of peak can be described as time equal to 2 pi divided by omega-1 minus the omega-2. So when the omega-1 approximately equal to the omega-2, the periods become very large, and it can be recognized as non-coupling. So it will vibrate in its own natural frequency. Here's the analysis about the level of obvious coupling. For the red part, which is non-coupling, when the amplitude is too small, the oscillation cannot be observed, which is defined in the non-coupling situation as in the previous preliminary experiment. And for the yellow part, which is non-coupling, because the distance is too short, the two lip spring will influence each other too frequently, which means the coupling is not obvious. And for the blue part, when the amplitude is different, it's recognized, and the peak in one bit is enough. So the coupling effect is most significant when the distance is equal to from 6 cm to 10 cm. And next experiment is about the length of the lip spring. So the peaks become sparser due to the natural frequency become lower while the length increase. And we also observe that the period of the beat decrease because the elastic constant also decrease while the length increase, which meant the magnet is easier to influence others. So here's I also pick out every peak in our experiment after I doing fast Fourier transform, because the both frequency decrease while the length increase due to the change in the elastic constant. So which causes the natural frequency to be different, influenced by the magnet, and can be more significant. So I analyzed the different stage in this experiment. So for the red part, which is non-coupling, when the amplitude is too small, the oscillation cannot be observed. And for the yellow part, when the lip spring is too short or too long, it has non-obvious coupling. So when the amplitude difference is recognized and peak in one bit is enough. So the coupling effect is most significant when the spring length equal to 22 and 24 centimeters. And next experiment is about the magnetic force. So while controlling the mass and the distance, which is the same magnitude, and if the magnetic force is small, the passive side of theta 1 cannot affect the motion of the driving side a lot because the repel force is too little. And the reason that the period of beat decrease while the magnetic force is because it's easier to influence each other. And I also pick out every peak. So when the magnetic force is too little, the coupling motion won't be significant, and the natural frequency will lag. As I mentioned before, the period will equal to this. So when the omega-2 will increase while the period of the beat decrease. So here's the conclusion of my report. First, why will the spring have a coupling motion? Because the repel force drives the passive side to move, and the passive side oscillates due to the spring natural frequency. And while the amplitude of the passive side increase, it turns to decrease the amplitude of the drive side, that this graph shows. And so next is how is the oscillating frequency changing in different parameters. So when the distance between the magnet change, for the period of the beat change while distance get different. So when their angular frequency is approximately the same, the period will become infinity, like this graph, like this formula shows. And the second, how the oscillating frequency change in different parameters. For the spring length, it will and the graph will be look like this. When the length of the lip spring increase, the angular frequency has a negative correlation to it. And next is about the oscillating frequency change in different parameters. So you can see that the omega 2 is a constant and the omega 1 has a positive correlation to the magnitude of the magnetic force, has a positive relation to the magnetic force. So what condition make the coupling motion most significant? For a length of the 27.5 centimeter, the coupling effect is most significant while distance is equal to 6 to 10 centimeter. And while the distance equal to 10 centimeter, the coupling effect is most significant when the lip spring equal to 22 and 24 centimeter. And here's my end of my report. Thank you.
So the first question I want to ask is, so I want to make sure parameters. So the parameters are the length and the distance, right?
Then the distance also the magnetic force.
How do you change the magnetic force?
We change different magnets and adding the mass on the top of the lip spring to ensure that the mass of the lip spring is the same.
Okay. So when you curve the leaf spring, it curves, right?
Yes.
And do you take that into consideration of your theoretical model?
Yes, we consider that it's Euler Bernoulli springs model that this series shows.
Oh, okay. Okay, I'll get it. And can you switch to page 17? Okay, how's the left graph related to our experiment?
Left graph, because we measure the Young's model, we can derive the Lassig constant of the experiment. Since that is very important because it's related to the potential energy of the lip spring.
Oh, so the yellow line?
Yellow line.
What is that?
Oh, because if we pull the lip spring down, the lip spring will deformation, and this is the after deformation, the lip string will be look like this.
Oh, okay. Wait, let's switch to page 22. Okay, what is the left top ring, the x and y axis? Can you explain that?
Oh, it's the peaks in one piece, and this is the M2 of the peak, and the unit is degrees.
Degrees.
Yeah.
How do you measure degrees? I mean, it's distance.
Oh,
Where's the origin?
can you use the blackboard?
Okay. Oh, well, okay. I think we'll get that. Okay. So, that's all my questions. Thank you.
14 degrees for around the law and the
Okay, so hello, we are Team Trivia, and today I'd like to oppose problem 6. So problem statement reads as follows. It is shown in the presentation of the reporter. And the key points we're focusing on are the mass and other parameters well controlled, and what are movements of the spring can be investigated. And most importantly, how is the magnetic force and the lead spring modeled? So here's an overview. And so for the overview of the report, the reporter has shown various parameters, and there's also a clear image and video of the apparatus. And also, he defines feet and other parameters at the start of the presentation. Now, for theory, there is a qualitative analysis and a complete theoretical derivation. There's also a very complete analysis of the lead spring, and it even considers the effect of air friction. So for the experiment, there are various parameters, and there's also well explanation of the data and analysis. So for the advantages, there's a clear and loud voice that successfully recreated the phenomenon, great experiment settings for the most part, and good time management, and also a very persuasive theoretical model which fits the experiment. So for suggestions, I think the reporter could have more emphasis on the parameter overview, so make an overview slide to let us know that what parameters you have done. And you could also focus more on the magnetic force model, because we're interested in how the magnetic force affects the motion, because the magnets are just, they are what makes this experiment different from non-applied magnets. So the equation shown on the reporter's slide is somewhat complicated, so I hope that the reporter can spend more time explaining those equations. And also, the reporter could have a video demo of the parameters. There's a video at the start demonstrating the phenomenon, but not for different parameters. There's only one video. So I think that there could be multiple videos which describes, for example, the non-obvious and the obvious case, what they are different. So here are the points to be discussed. Can I please invite the reporter? So for the first question, so you see that the lead spring oscillates in sort of simple harmonic motion, right?
Yes, it has. The force is a function of the distance.
So it is just like a normal spring.
But can I use the blackboard?
Okay.
If we use the normal spring, the coupling situation will be like this. It's like this spring, and this mass. It's an object, and this also a spring, and this also another object. And here's the base. So when sometimes in this situation, the force will attract it and repel. But in our experiment, the magnets always repel each other. So the ruler will also play an important role in this fluidness.
But like for a spring, it can repel and attract.
Yes.
So how do you change the spring model into the magnetic force model?
We use Lagrange equation to change the model, and by solving the equation, the numerical solution will fit the experiment very well.
Okay, so how is the spring model related to that?
Since that is the coupling situation, the spring in these two kind of conditions, both of them are coupling system. So I think that it's not directly related to our experiment model.
So it counts in your theory.
The only point in our model is that the potential energy of this part is, and it can be regulated as this formula.
Yes.
And but since that is not a normal spring, so please turn to like this part. Like this part shows. So we calculate it. So we derive it again, since that is not a normal spring.
Yes. Okay. So is the lead springs? Well, can the lead spring apply this formula?
No.
No. Okay. So it's just
it will be a simple model, but I think that it cannot be enough to explain this phenomenon.
Okay. So let's move on to the next question. Can you have more emphasis on the magnetic force? How does that play a role?
How
For example, how is the magnetic force calculated? What is the expression?
We use Gauss meter to calculate the magnetic force. Like if the magnet is like here, we measure every dot here, use the Gauss meter to find the function of the magnetic force and the distance.
Yes. Okay.
Yes.
So what power is this? So what is the solution? So for example, the magnetic force.
When the distance increase, the magnetic force will be smaller.
Okay. So what is the power? Do you find that, or do you find another?
I think it's not related. It's not directly related.
Oh, okay. So you find a function for the force.
For the magnetic force, yes.
For the force.
Yes.
And so can you briefly write the equation? So what is distance? So you mean this is not important. The power is not important.
The power is not important.
The power of the distance.
It's an important role since that we have also do experiment to measure that the distance also will also affect the cold plane situation.
Yes, it affects.
Yes.
Yes.
I cannot directly. I think this not directly affect cannot explain our theory.
Oh, okay. So how does the magnetic force, the relationship you derive, how can it support you?
I calculate the magnetic potential energy like this.
Okay.
In the final part of the
So
graph.
you have a position already, but not force.
Yes, I use since the Lagrange equation can use energy to calculate the equation of motion.
Okay. Okay, so for all of these three models, can you briefly explain how the Young modulus plays a role in your equation?
Since that the measurement, please turn to page 17. Since that we can derive we can get the relation between the Young's models and the elastic constant by using the deflect curve equation.
That kind of equation.
Yes.
Okay. Okay. So you said you control the mass of the leaf spring, right?
Yes.
And how do you control that?
Mass of the leaf spring. I control the top mass of the leaf spring and to make sure that the total mass of the leaf spring is the same.
What do you add on the top?
What do you add? Non-magnetic material.
Like what? Can you
Like plastic or like something that can add in the waste or on the ruler. Like plastic or yes.
Okay. So does that affect the air friction or other factors?
I think it will affect a lot since that we make sure that the theory fits our experiment.
Okay. So is there an image for the?
Since that the air friction only relate, we write a function as which is the coefficient multiple the area and the velocity of the area will equal to this.
Perhaps squared?
Squared?
Oh,
No, I think
okay.
yes.
Okay, so is there an image for how you control the mass or is there not?
Control the mass.
Yes, how do you, what do you add on the spring? Is there an image or no?
Image?
Yes.
No.
No,
We
okay.
didn't show it.
So, okay, so do you think there's magnetic energy, right?
Yes.
There's also kinetic energy.
Yes.
How do you think they're exchanged in the experiment?
So please turn to the okay. So as I mentioned, there's the one left spring and there's another one. So when I bending the left spring, it will store the elastic energy, and it will the system will try to recover in the initial position. But the kinetic energy of this spring will transform into the potential energy and another elastic potential energy of another leaf spring.
Okay.
Yes.
So is there energy loss?
Yes, the energy loss caused by the air drag.
Oh, okay.
And also the setup, we control here to ensure that there will not be other vibration or unpredictable oscillation on the base of the disc spring.
So you think the decay is purely due to air
Yes.
and not due to the friction of the base?
No. Since that we control here. So I think that is not important. And we also measure the effective length of the Ullmann Bradley bridge by measure the here from here. Since that you have mentioned in the discussion in your short question, you asked that how we calculate the
That's our next question.
okay. How we calculate the angle. So when the spring is bending, it will be look like this, and the tangent and the centimeter will be like this right here. So the tangent the tangent line of the top will their including angle will be the theta in our experiment.
Okay, so how do you find the positions of your leaf spring?
By the
Do you use
position.
a tracker or?
Oh yes, we use the Arduino.
Oh,
to-
yes.
yes.
So on which point of the leaf spring would you
Uh,
place the?
We add the magnet on here.
Yes.
So we also add the Arduino sensor in here.
So I guess it's here, right?
Yes.
So you know the position of this.
Yes.
You know the position here.
Yes.
But how do you know that if the leaf spring is actually like this? What if it's actually like this and the tangent line is here? So that thing is different.
Oh, we measure it and calculate by our program. Since that we use Arduino.
Oh, so you only know that
And we
this is,
also use tracker to make sure that our theory is correct.
but you only know the distance here and here. You don't know what's happening.
We can calculate by our program and computer.
So you assume that your program and computer and theory are correct.
Yes.
Okay.
And also the experiment, yes, did very well.
Okay. Okay. So. Okay. So how do you know the natural frequency of your leaf spring?
Natural frequency. We measure the natural frequency since that we use the hand to vibrate and finally giving the natural frequency
So I think it's for the non-coding case, right?
non-complete case. Yeah, right.
Okay. Then can you switch the slide?
Yes, because yes.
Okay. So how far are these springs?
How far is the string?
I
We
think
didn't
it's,
measure. It's I remember that is 17 centimeter.
Oh, so this spring is non-magnetic, right?
Yes,
And there's no magnet on it then.
on the left. Yes, yes.
Okay. So. Oh yeah, another question. So you said there are boundary conditions for the non-magnetic or non-obvious coupling and obvious coupling.
Yes.
So how are the numbers chosen?
I think because the distance will change the magnetic force.
Yes.
When the distance increase, the magnetic force will decrease.
Yes.
So I think that the magnitude of the magnetic force is a significant factor that affect the coupling situation.
Okay, what I mean is the wait, can I switch back like one click? Okay. So what is this number 6 to 15? How's it chosen?
Oh, we just the definition to help us to can easier analyze the experiment.
Okay. So did you find? Oh yeah, you find out boundary condition.
Yes.
So you said that on page 25. Okay. Can you switch to page 25? Yeah. So you said that 22 to 24 centimeters has the best coupling.
Yes, it fits our definition.
Yeah, but can you switch to conclusion? Is there a conclusion? Yeah, I think that
Yes, when the left spring is equal to 22 and 24 centimeter.
oh okay. Oh yeah, I think that's fine. Okay, let's see. Okay, that's the end of our quote. Okay, so can I summarize the discussion? Okay, so in this discussion, we first talk about how the single harmonic motion and the spring model relates to the reporter's theory. And also, we also talk about how the mass of the spring is controlled and other various parameters. And we talk about the kinetic energy and the potential energy or the elastic energy exchange and the relationship with the magnetic energy. And the reporter also says that how they measure the angle, but I think there's a flaw there, so I think we'll talk about that later. And yeah. Okay, so okay, and we also asked the reporter about how the magnetic field is modeled. So we asked about this equation, but they didn't give us the relationship. However, they said that they know the expression for the potential energy, but not for the field. And they use the field to fit their theory and find that the theory is complete. So.
Thank you for reporting and John and I'm the reviewer of this session. And the first question I'm going to start with the problem statement. So the problem statement mentioned that you have to use two identical lift springs. So what is the purpose of the identical?
The identical things that it will have a coupling motion. Since that if the two lifting connect together, it won't have a coupling
Okay,
situation.
understood.
So I think the identical means that there's homogeneity in the.
I mean, what's the purpose?
The purpose is to make the analysis simpler.
Okay, so now move on to the theory part. So first question, could you please briefly explain what is the beat frequency?
We define it as the in the top of the two peaks of the
And how about opponent?
You mean the theory?
Briefly answer what is the beat frequency?
The frequency is shown on the slide, and that is the distance.
Okay, since the reporter considered the bending, right? So you mentioned you have to control the mass. Do you think you have to control the total mass or the effective mass?
Since that we control the total mass.
Okay, how about
I
opponent?
think the total mass and the Matthew energy are the same.
So you mean you both think you have to control total mass? Okay, so please turn to page 12. So can the opponent answer? Please explain what is this theory talking about?
This theory talking about is using the Young's modulus to model the D-spring.
Okay, so do you agree with the opponent?
Partially agree since that we calculate the total kinetic energy of the lift ring and the potential energy.
I understand. And turn to the 13, please. Okay, so as we know that the magnetic field is not uniform, so is it appropriate to use this equation in this situation?
I believe that it's suitable for our theory
Okay,
and
how
our
about
experience.
opponent?
Because the magnetic field fits the theory, so I think it is. I agree with this.
Okay, so now let's move on to the experimental part. So you mentioned the experiment is not appropriate to a small, when the magnetic field is too small, right?
Yeah.
Yeah, so how about the magnetic field is too large?
When the magnetic force is too large, please turn to page.
How about the potential? I will come back.
I don't think I see that in the experiment.
What do you think will happen with if
I
the?
think the coupling will be more obvious.
Okay.
I think that when the distance is too small, which means that the magnetic force is increased, it has a non-obvious coupling situation.
Okay, I got it. And here's your graph, right? So what's the meaning of this?
I think
coefficient?
it's the last constant, and we can measure. I think it's the function of deflection and the force.
And what's the basic meaning of this coefficient?
So they calculated the parameters for the model, so to fit their model.
Okay, so can the opponent answer why is the place that stop is not at a 0 point?
Because the magnitude has.
And how about report? Okay, thank you.
How many of your
Thank you for reporting and the review of the decision, and I'm going to review question number 6, magnetic mechanical oscillator. And here's the problem statement. And we basically focus on the movement of the spring, and also I think the identical is pretty important, and the test fulfilled is partly fulfilled. And here's the summarize of the presentation. So they main focus on the movement of the spring and the frequencies. The theory is the Lagrange equation and the Euler's law. And the setup they use is pretty good, I think. And they also use the repomagnetic and the leaf spring and the motion sensor, and also the motor. I think that's appropriate. And the parameters that they did is the initial distance, the length of the spring, and also the magnetic force. And here's the conclusion of the reporter's report. So here's the pros and cons of the report. I think he could explain the quantitative phenomenon explanation and a lot of experiment to prove his assumption, and also well modeling on this spring, and also good experimental setup using the motion sensor. I think it's pretty well. And for the cons is that consider the bending but not consider the effective mass. That's the reviewer think it is most important thing. And also lack of explanation of the phenomenon, and didn't mention what the purpose of the identical magnet. And here's the pros and cons of the opponent. The opponent point out a lot of points that the reporter has misunderstanding, and also ask about the magnetic field, which the reporter didn't explain. What about the cons is that they didn't ask about the bending in the equation, and didn't ask about the misuse of the Lagrange equation. And here's the discussion point of the reporter and the opponent. The opponent asked about, do you consider the bending? And the reporter answers that they consider the bending is very important. And the reviewer thinks that the reporter used a model for bending, but didn't consider the effective mass, so which is an important characteristic of the bending. And here's another discussion point. The opponent asked about how do you measure the magnetic force, and the reporter answers that use the gas measure to measure the magnetic forces in every position. And the reviewer answers that the reviewer thinks when the magnet is of the spring should be considered as the effective magnetic force. And here's another discussion point. The opponent asked about, do you only consider air resistance in the resistance? And the reporter answers yes. However, the reviewer thinks the air resistance shouldn't be the only resistance, since the connect point should be cost damping. So it should be also taken into the consideration. And here's another discussion point about the opponent asked about how to measure the angle change. And the reporter answers that they use the initial displacement and the length of the leaf spring. However, the reviewer thinks if the reporter considered angle of their in their equation, the mass should be replaced as the moment inertia. So here's some mass point the reviewer would like to point out. The first one is the reporter considered the spring as bending, but not consider the effective mass, which is most important characteristic of the bending. And also, since the problem statement mentioned identical leaf spring, and they didn't, both the opponent and the reporter didn't mention what is the purpose of the identical leaf spring. So I think that should be point out, and wrong definition of the beat frequency. Since the reviewer believes that the definition of beat frequency should be the difference between two frequencies, then they can combine together and have the beat frequency. And the last missed point is that the reporter analyzed the trajectory of the angle, but not measuring the moment inertia. That the reviewer thinks in this situation, the moment inertia should be mentioned in the reporter's report, or the opponent should be asked about this question. So here's all my presentation, and thank you for the reporter and opponent.
And here's my concluding remark. First, we measure the Young's modulus to calculate the elastic constant to calculate the potential energy, since that we use it in our Lagrange equation. I also use the Lagrange equation to calculate angular acceleration of the two leaf spring, and we also solve the equation of motion. And it's not like a normal spring, because the magnetic force on the another leaf spring is always a repel force. And the energy loss mainly caused by the air drag. And there has some little deviation is come from the consumption of our setup, but we cannot calculate. And we define as the obvious coupling as 6 to 15 peaks to analyze the experiment easier. And our our theory matches the experiment very well, and we use Gauss meter to measure the magnetic field. And when the magnetic force is too big, the leaf spring will experience not obvious coupling, since that when the magnetic force is too big. And we control the total mass of the leaf spring, and we use the we use because we control the total mass of the spring, so we control the transition energy, not the rotational energy. And we also solve the equation of motion, which is the angular acceleration in the report, and we also consider many things that we use Euler Bernoulli spin. Thank you.
I would like to see the low bread by the repulsive force between the magnet. If instead you break the polarization of magnet and it becomes attractive, then what different consequences?
Can you rephrase your question?
That is the repulsive force between the magnet.
Yes, it will just attract it together, and it will not have a coupling situation.
So no more force.
No.
So the question is that if the magnets are attracting, I think there will still be the coupling. I think there will still.
The reverse thing is when the magnetic field is too small and it will cause the coupling motion. And especially the symmetric mode.
So for this damping, besides this air drag, what would you consider the importance of this eddy current damping?
Well, the reviewer believes that because the magnet will move in the magnetic field, so it will cause a eddy current. So the eddy current will cause the energy loss.
Eddy current might happen in our series things that we didn't consider, but I agree that it also causes a deviation, but we didn't consider it in our report.
Yes, I agree with both because the magnets are acting metal, so there will be eddy currents which will cause heat loss.
Thank you.
Thank you.
Can I have one more question? Because in all this presentation, I don't see a clear simple physical insight what determines this beating frequency.
Because it has because the magnetic forces affect each other. So I think there will be a coupling constant. By fast Fourier transform, we can get two angular frequency of it, and which is that the bit frequency.
The reviewer believes that the bit frequency is the difference between two normal modes, and the coupling is the combination of two normal modes.
From the report, I think I learned that the bit frequency is the time distance, the time gap between two key points. So I think that's obvious and easy to understand.
Thank you.
Thank you.
Apollo 76886. Reviewer 88887. 10 minutes for break.
不需要，还好不需要。对啊，对，要看校长，看他们觉得很重要啊。不想就完，或者把工学的老师系上，这一学期的，没有他一个学期，我就不要他，让他都几年级，让他上去教下去，然后那学上。没有，所以他们也是这样搞的，因为我们的是可能好一点，我们讲的
I'd like to challenge problem number 11.
11. Adele J. Author. We reject. Reject. Reject.
I would like to challenge problem number 5, disordered mesh.
Number 5. Reject.
We would like to challenge problem number 9, oscillating screw.
Number 9. With that, we get me.
We would like to challenge problem number 2, oscillating sphere.
Number 2. Very right down your name.
消失时的航线。
Okay, I'm ready.
Okay.
So hello, we're Team Trivial, and now we'd like to report problem 2, oscillating sphere. So the problem statement reads as follows. A light sphere with a conducting surface is suspended in a thin wire. When the sphere is rotated about its vertical axis, directed in the wire, and then released, it starts to oscillate. Investigate how the presence of a magnetic field affects the motion. So here are a few parameters we investigated. The first is the radius of our spherical shell, and then is the applied current strength, and also the magnetic field. And then is the length of the wire, and then is the material of the shell, and kappa is the torsion constant of the wire. So this is the material, and this is the kappa, torsion constant. So here's an overview of our setup. So for our experimental setup, we have the cable, wire, and these apparatus. So on the right is an actual image of our apparatus. You can see that the camera is placed under the tempos coil to prevent damage to the camera. And all the other apparatus can be seen in the image. So the tempos coil is used to provide a horizontal magnetic field by this equation. However, we will not use this equation and use our experimental basis to find the magnetic field. So we use tracker to analyze data, and we have a tracking sticker here to track the angular motion of the ball. Here's our tempos coil, and the shell here we use is a copper plastic shell. So for our setup, this is a close-up view, and you can see here, this is how we suspended the string. The wire is clamped in 3 directions and suspended from the cable. So for the phenomenon, on the left is the details, and on the right is an image of our apparatus. So this is the phenomenon. So the theta here, or the damping effect, is hard to see, but you can see that there's this sort of angular oscillation. Okay, so there's angular oscillation, and we want to analyze the data. So we can draw angle position versus time graphs of 2 cases, with magnetic field applied and without magnetic field applied. So we can draw these graphs, and we can analyze the peaks of these graphs. So the peaks will be attractive. And then we can calculate the amplitude of each peak. And then we do an exponential fit. So when you do an exponential fit, we have a time constant. The smaller the time constant, the slower the decay. The larger the time constant, oh sorry, I think I put it opposite. So the larger the time constant, there is a slower decay. Okay, so the result for the phenomenon is that the group without external magnetic field decays slightly more significantly. However, this result is overturned by more accurate experiments later on. So for the theoretical model, first we consider a freely spinning shell in a horizontal magnetic field. So for the reference, we find that in such magnetic fields, the shell will experience a torque T, which is given as this equation. So then we model the damped torsion pendulum. So on the left is a normal torsion pendulum, on the right is a damping term. So if we define these 2 quantities, we can solve the differential equation as follows. And then we can obtain a general solution. Now, if there's extra damping caused by the magnetic field, there will be an extra damping term, which can be solved very similarly. And we find that the similar solution has a smaller time constant. Therefore, our hypothesis is that the group with external magnetic field will have a larger time constant, which means it will decay slower. So for the experiment, first we measure the distribution of magnetic field strength of the Helmholtz coil. This is the side view. The radius of our coil is 14 centimeters. So we can, when we measure the magnetic field, we find that these 4 regions have different magnetic field strength. And we analyze for 3 different kinds of currents. You can see that in the dark blue section, the magnetic field is the same. So we find that the magnetic field strength in the shaded area here differ less than 10%. Therefore, we will neglect fringing effects of the coil. So this is our experiment process. So we're filming, we film from below, and we have a tracking sticker to track the position. And the video settings, we record at frame rate of 30 frames per second, the resolution is 720p. And we use auto tracking of the tracker. We use tracker's auto tracking to minimize error. So when finding the angle, we manually fit a protractor onto the tracker. So we fit a protractor here to find the angle. And the angle data analysis is code-assisted, as we will see later. So this is all the data we analyze. This is the tracker data, and this is the data that we further analyze. So first, we correct the angle. Because there's negative overflow when the angle gets too large, we have to fix this overflow. So we use the program to do that. So before and after. So then we analyze the peaks. This is also easily done with the program. So before and after. So we find that these points are non-peak points shown in this graph. So we manually remove them. Now when the amplitude gets too small, the climax points seem to be hard to recognize. Therefore, we also manually remove data from here on. So we want to find the equilibrium angle. So we can use this formula to find the equilibrium angle. And then after finding that, we take the average, take the average of the middle value, and then calculate the difference. That is the amplitude or deviation. So before and after, basically we calculated the amplitude. And then we use exponential decaying curve fit. Okay. So for example, in this data, we can find the amplitude, time constant, and the correlation coefficient, which is usually very common. So first, we investigate the effect of different magnetic field strength. The independent variable is the applied current strength, or the magnetic field. So we can analyze the current applied to magnetic field, the oscillating period, and calculate the uncertainty. So we find that the oscillating period seems to be constant. That is the oscillation period and not a damping. The oscillation period seems to be constant with very magnetic field, possibly due to the fact that the change in the angular velocity is too small, given here. If we have time, we'll get into the theoretical derivation of that. So for the effect of different magnetic field strength, we can then analyze the time constant, that is how fast it decays. We find that there is this sort of relationship. So here we examine one. Below is a theoretical analysis of the time constant. So this is the equations from our theoretical analysis. We can find the small gamma, and for the theoretical model, we can calculate these quantities. So the final conclusion is that the reciprocal of the time constant has a quadratic relationship with the magnetic field. So if we just take a log plot of that, we would expect a slope of 2. So we can then calculate the quantities, that is the reciprocals, and then calculate the log values. And then after that, we'll do a curve fit. The slope we obtain is around 1.6. So there are various things we can say about this graph. So for the y-intercept, from our equation here, it is log of k prime. So log of k prime, we can find k prime. Now here we will do a simple theoretical calculation of the k prime. So k prime is defined here before, and we can substitute k from the theoretical model. And for the quantities, we have these quantities that we can substitute into the calculation of the rotational inertia and the k prime. So we can see that on the right is we can recall what these symbols mean. Okay, so k prime in equals 550 is for the magnetic field in Tesla. So you can see K and magnetic field are related on the right. So if the magnetic field is in millitesla, then K prime would be adjusted to this value, which is similar to the theory value. So here we examine the effect of different materials. So our second material is a copper tape. So we put copper tape on a 3D printed shell and styrofoam shell. You can see that the resistance is significantly higher when we measure the resistance across the shell. So these are our copper tape shells. And this is the result. So you can see that the time constant doesn't seem to have that descending trend. So the result, the decay is insignificant. Now, the effect of different shell sizes. So we have a radius of 100 millimeters copper shell. So we can then do a similar analysis. We use different currents, and found different time constants. Note that time constant here is significantly larger. Now, we can also calculate the uncertainties. We can then do a similar analysis to find the reciprocal of the time constant and take the log values. And this is the equation we have seen before. We can do a similar bit, and we find that the slope is around 1.3. The theoretical slope is 2. So here are reasons that we think why this error has appeared. So the graph slope has an error because the data all depends on the I equals 0 case. So you can see here, all the data has to be subtracted by the reciprocal of the time constant when there is no magnetic field. So if that data has a little bit of error, the slope will vary. So as you can see here, when it's varied by around 12, the slope will be equal to 1.6, and when it changes by about 20, the slope is ideally 2. So for a conclusion, when applied a perpendicular magnetic field, the torsion pendulum will have additional damping, as shown in theory. The more conductive the shell material, the more significant the damping effect. Also, larger shell size have more significant effect on the time constant difference. So for further insights, we think that this experiment could be further investigated with larger shells or higher magnetic field strength, which we expect the phenomenon to be different. And also, this phenomenon could be used to de-spin a fast rotating astronaut or object in space type of spaceship. And that is my presentation. Thank you.
Thanks for the presentation for the reporters. I would like to ask some questions. Could you turn the page for 11?
11?
Yes. Yes. Could you tell me the ball is hollow or the solid?
It's hollow.
Is it hollow? Okay. And did you measure the thickness about your spherical shell?
For the cover shell, yes. For the cover plate shell, no.
Okay. And about which kind of damping did you think is considered in your? Which kind of damping did you consider in your presentation about the damping motion?
And you mean what parameters of damping?
Since the damping has the 3 types of damping: critical damping, under damping, and over damping.
Oh, okay.
So which kind of damping did you consider as your trajectory of the theta?
We consider the so this also is a motion. I forgot what the name it is, but it is the solution where the determinant is imaginary.
And I believe that the damping in your trajectory equation, I will believe that it is under damping. Okay. And another question is, please turn your page to 55. So, is that the real error that is quite large, that some of the data will over the magnetic field for
Yes.
two? Okay. I would like to discuss further. And do you do the experiment with no magnetic field?
Yes.
Okay. Another question that I would like to ask: did you know the direction? Do you know the main reasons that cause the ball resistant by the magnetic field?
You mean there's a damping?
And the physics picture behind this phenomenon.
Sure. I don't get what you mean.
Okay. Do you know that the conducting object will moving in the?
Oh yes, the eddy currents.
Yes, the eddy current. So I would like to discuss the direction of the eddy current further.
看一下。
好
Okay, honorable juries and fellow competitors, I'm Ethan Xu from Team Epsilon, and I'm the opponent today, and to talk about problem number 2, oscillating sphere. So in the problem statement, I think the main focus of this problem will be the conducting surface of a suspended with a thin wire, and then it will rotate in the magnetic field. And so as the main question about the problem statement, I will focus on investigating how the presence of the magnetic field affects the motion, and I believe we will discuss it in our discussion time. And about the summary, that the theory they used, they calculated the trajectory of the damping, and I believe the reporter can mention that the damping that they consider is the underdamping, and the tangent pendulum to calculate the equation of motion for their phenomenon. And about the experiment, the setup they use a conducting, they wrap the copper paper on the hollow sphere to create a light sphere like the problem statement mentioned. And they use a coil and they measure the different positions of the magnetic field to make sure the ball will rotate it in the uniform magnetic field for the calculations. And about the parameters, they use a different strength of the magnetic field and different conducting materials on the magnetic field. And about the method, they use Python, tracker, and magnetic field sensor to measure the magnetic field, how's the uniform of the magnetic field. And about Python, they use the Python for analyze the trajectory about the theta. About the conclusion, they mention that the magnetic field will create a damping, and the more conductive the material is, the damping will be larger. And the phenomenon could be used to spin the fast rotation object. And here's some strength and the area for improvement about the reporters. About the strength, they have completely quantitative phenomenon explanation that they mention the magnetic field will create a magnetic torque that makes the balls spin. And a lot of experiments to prove the assumption that they have a lot of error bars, so I believe that they do a lot of experiments for the presentation. And they have a good experimental setup that they control the rotation in the uniform magnetic field, and they use they make sure the magnetic field to make sure it is uniform. And about the area for improvement, they have lack of quantitative comparison between theory and experiment, and they have a clear physics picture that they didn't mention about the direction of the eddy current that provide the run force that make the balls spin. And they have an unclear graph explanation. I think I will discuss in the discussion time, and they didn't have the error analysis in some of the results that have a lot of large range about the error bar, and they didn't show the blank experiment for the origin damping, and that I believe will be the zero magnetic field damping, that they can make sure the generalized damping terms, and they could explain the mechanism behind the damping more, and they could categorize the magnetic field in this system. Since that the problem statement mentioned that the reporter should be main focus on the presence of the effect of the magnetic field, then I believe they will create eddy current that makes the ball resist. So the tactic for film, I will say the reporter have partially for film in their presentation, and I would like to move in the discussion. So please turn to page 55. I did explain why the error bar has a large large area in the experiment about the.
Okay, so
55.
how the error bars are calculated is when we do an x. Okay, so you know how we calculate time constant?
Okay, I know.
Yeah. Okay. So when we analyze the time constant in the program, we use Phi Davis to calculate the okay. So the time constant has it comes with an ability.
I would like to ask is why does the magnetic field increase and the errors will also increase?
Okay. Oh, I don't think that's at the end of it, you see, this is small and this is large.
Yes, I would like to ask the reasons that why the magnetic field increase and error will also increase. Maybe there's some reasons behind a relationship between the magnetic field and your error.
I don't think there's a trend. I mean, like for 1.5 milliteslas, the error is small.
Yes,
But
and
for zeros,
for 3 micro Tesla,
okay.
for why does the error bar has so large area?
Because it is calculated, and I think maybe because the oscillations are not, the period are not stable.
So in my opinion, I think maybe when you add more magnetic field,
that will make the ball resist. The ball will more sensitive with the magnetic field that you provide. That makes the damping current that you calculated will have some errors. And so another question that I would like to ask about that you mentioned, the eddy currents are provided by the magnetic field. Could you tell me the direction?
Direction?
Yes.
Direction?
Direction about the eddy current.
Okay, we did not actually investigate that because in calculating the formula, it goes to the theoretical derivation. We did not use any current to calculate. Okay, so here we can see. So, okay, calculation. Okay, so calculation. We did not use any current. In fact, we used Maxwell's first equation to calculate charge density and then the current.
Okay, I understand. But in the next page, you show a picture.
Oh yes.
About the sphere. And I believe the direction is the direction of the eddy current in the reference.
Yes.
So does the direction of the eddy current correct? In what do you think?
Okay, so the shell rotates here. I think that's you got it. So
maybe we can move on to the backward and we can draw about the eddy current together. Okay. So first, we can assume that the eddy current, the direction of the eddy current that the reference provides is correct.
Yes.
Correct. And then we can draw a sphere. We provide a uniform magnetic field here. And so, if the reference is correct, the direction of the eddy current will move on this side.
Yes.
So far so good.
Well, no, I think.
So where did you provide the magnetic field?
Oh, it's on the z-axis. Yes.
So this is correct.
Yes.
So since that to find the relation in the sphere, direction of the sphere to find the force, I think is very hard. So do you think that it's okay to take a part of the sphere for the discuss? Since there can create eddy currents along the sphere. So let's take a part of the sphere to discuss.
Okay, so your point is that you're telling me how to analyze
the reduction and the torque. Okay, let's talk about it. And so we take this part. So we assume that the balls only have the one rings for the conducting surface. Okay, and so the direction of the eddy current is in this side, correct? So so we can assume it as a loop. That's the eddy current, correct? Is that okay? And so that we create the B field this direction. So let's talk about the direction of the Lorentz force. Since that I think the main reasons that cause the ball resist will be the magnetic force that's acting on the sphere, and it will relate it to the magnetic torque. So if we take a ring for discuss and we have correct about the direction of the current. Okay, then let's talk about the direction of the magnetic force, which is I would like to discuss about Lorentz force. So far so good?
Yes.
Okay, and we create the coordinations. And we here's the side view. And if we look the currents in up view on the top view, that the current will go inside this direction and go out but go inside in this direction and go out this way. Okay. So we can draw here's the up view of the current that you provide. And here's the magnetic field. And so could you tell me what is the direction about the force that moves on the sphere?
Okay, so the current is this way. The right-hand wall.
Yes, we use like yes. So we take the hands together for the right hand. We can found that the direction of the Lorentz force should be in this direction.
Yes.
Yes. Direction is this side. And from this side will be the opposite side. Yes. So we clarify the direction of the Lorentz force, we can find the torque. So as we know there is the force acting on the sphere, we can know that there is a torque. And I believe that the torque will be proportional to the angular velocity. That's makes the ball resist. Negative angular velocity. So that's so if this is correct, that we can mention the presence of the magnetic field that works on the sphere. Yes. So that's in our discussion we still define the direction of the force, and we measure about the torque in the simplified physics picture that creates an 80 field. So can you tell me if we take the part of the sphere only in the parallel to the magnetic field, what will happen there?
Well, I think there's symmetry, so I think the total force will be zero.
Yes. Okay. Then let's discuss about that. We take a part of the parallel.
Okay.
Part of the parallel. So could you tell me the reasons that the reasons that you think the Lorentz force will be zero?
Because we are going to go this way. So
Yes.
this part comes here.
Yes, correct. Yes, I agree to the reporter. Since I think the 80 current will related to the magnetic flux that in every single moment. And if we take a parallel part of the conducting surface, that the flux that in these cases will equal to 0. So which means there's no 80 current. Okay, let's move back to your translation. Did you measure the original damping coefficient in your presentation?
Oh, the original damping position, yes. So the original damping position is described by the lowercase gamma. So here's the configuration. Okay. So you see that it's gamma here?
Yes.
That's the original damping.
In your experiment,
Yes.
you measure.
Yes, we calculated it later.
Okay. And how do you combine the original damping terms to the magnetic damping terms together and to comparison between each other?
So the magnetic damping term is just shown here, and it's just an extra damping term. So we can calculate this one, the uppercase gamma.
So did you have the comparison in your experiment?
Comparison?
Did you measure the magnetic damping terms in your experiment?
Oh yes, we actually did a brief calculation on that. So, oh wait, yeah. So, yeah, this is how we calculate it.
No, for experimental result.
Oh,
Did you calculate the magnetic damping terms since you can calculate it
Yes.
as your theoretical analysis?
yes.
So did you use the experimental result in comparison with the theoretical
Oh yes, we
calculation?
compare the K prime values. Remember?
And could you show that the comparison?
Oh, yes, here.
So did you
K prime value.
okay, do you have comparison with the theoretical magnetic damping terms in your experimental magnetic damping terms?
Yes.
And did you ignore the original damping terms caused by the rotating poles that in the zero magnetic?
Well, just consider.
You have considered in it for the comparison.
Yes.
Okay, and I would like to ask, did you think that if you ignore about the general damping terms, that can be more comparison between your theoretical model
So I think we should remove the
original damping terms since you have mentioned measured?
No, I don't think we should remove it.
Okay, and so the next question that in the presentation mentioned, which type of string that did you use in your experiment?
So string?
Yes, the wire that you connect.
Oh, it's nylon, just like fishing.
So do you think the wire is necessary in the since that the policy
Yes, I
mentioned?
think the wire is necessary.
So did you calculate the moment inertia of the wire? Do you consider it?
No.
Okay, here's my question. Okay, thanks for the answering question about the reporter. In our discussion, first we talk about the error analysis about the reporter's error bar. And then we talk about the actually presence of the magnetic field works on the sphere. And in that we have on the same page that the magnetic field that we provide will also, because the Lorentz force then provide a magnetic torque that we will proportional to a negative angular velocity to make the ball recede. Since the reporter didn't mention in the presentation about the reasons that actually make the ball recede in the magnetic field. And we also discussed about the damping terms that which kind of damping that the reporter considered in the presentation, and I believe, and is the under damping motions, and we asked about ignore about the original data.
所以你
Okay, so first of all, thank you for the discussion between the opponents and the reporter. So for both of the reporter and the opponents, what are the forces that cause damping when there is no magnetic field?
I think it's the wire.
The wire, what are the forces?
For the friction force.
Okay, friction. And
I think the connection between the different materials.
so what are the force?
So I think the friction will be the one of the reasons that the both.
And what is the other reason?
The other in
Because you mentioned one of the reasons. So.
also I think the air resistance should be also
Okay.
considered since the boat is
Okay,
a
thank you, thank you. And for both the reporter and the opponents, do you think with a hollow or solid sphere will cause a bigger phenomenon?
I think a hollow sphere will cause a big phenomenon.
Okay, thank you.
I think the hollow sphere and solid sphere will also will have a difference.
Which one is more significant?
So I think the eddy current will
Which
work
one
on-
is more
I think the
solid or-
hollow will more
Okay, can you
significant.
explain?
Since that the eddy current will work on the surface of the sphere.
Okay, thank you. And for the reporter, if the magnetic field is parallel to the rotational axis, do you think there will be a phenomenon?
No.
No. Okay. And do you think the eddy currents will only be on the surface of a sphere, or also in the inner parts of the sphere?
Only on the surface.
Only on the surface. Also, so in your theory, you mentioned that you calculate a time constant. Can you give me a definition of time constant?
So time constant is the measure of decay.
Yes.
The larger the time constant, the slower the decay.
So what is the definition of time constant?
It is.
Like, and when it's reached what value of the oscillating angle?
Oh, it's a curve. It's not an angle.
Okay, thank you. And for reporter, you meant in your video that you release a sphere by using your hands.
Yes.
And can you explain what will it cause? Will it cause any experimental error?
Yes.
So did you ignore it or?
Yes, we ignore that error.
Okay. Also, in your experiments, that you use a copper tape, right, to wrap the sphere, and the surface of the sphere will become uneven, right?
Uneven. Yes.
And do you think that this experimental method will cause?
I think
deviation?
it will be deviation since the eddy current will work on the surface, but I think that
So-
is not the necessary importance
Okay.
about the error.
So you think that the uneven surface won't cause a big deviation?
I think that
A big deviation.
the big deviation, I don't think, since they wrapped it as kind of smooth.
Okay.
under experiment.
And in your summary, you mentioned that the wire, the rotation inertia of the wire. Can you?
I think the rotation inertia of the wires, if they consider in their theoretical model, they will
Probably,
be
I
more
think,
correct.
in my opinion, I think it's a portion constant, not the
Okay,
rotation.
I think that both of them should be
Thank you,
considered.
thank you.
那你第二。 for
On the trees and all the commander, I'm the reviewer from Team Excelsior, reviewing problem number 2, oscillating sphere. This is the problem statement. A light sphere with a conducting surface is suspended from a thin wire. When the sphere is rotated about its vertical axis, it's thereby twisting the wire and then released and start to oscillate. Investigate how the presence of a magnetic field affects motion. So due to the problem statement, we mainly focus on how does the oscillation of the sphere act, and how will the magnetic field affect the motion. Also, some relevant parameters that will affect the oscillation of a sphere. This is a review of the report. So in the phenomenon explanation, he mentioned damping with a magnetic field, and in the theory, he calculated a time constant. And also, he calculated interchange, and the experiments, he did several different parameters like this. And I believe that he gave a very clear demonstrative phenomenon. Also, he has a clear explanation of the theory. However, I believe that he lack of analysis on the forces, including Lorentz force or friction. And he lack of graph about the experimental data and the comparison. Also, the explanation of the deviation here. For a review of the opposition, I believe that he noticed the lack of the explanation of the direction of the forces. Also, he points out that the reporter lacks of the explanation of and which kind of damping it is. However, I believe that he didn't discuss the conductivity and how will it affect. Also, he spent too many times on the direction, and that missed the points of the report. Also, he didn't give the reporter time to explain the phenomenon. So this is the key direction, the key discussion. And the opponents asked what is the direction of eddy current, and the reporter didn't give a clear answer. So the opponents explained that on the backboard, and the reviewer believed that the eddy current flow will make a circular direction. So with a magnetic flux, it will create a magnetic field in this direction, and also the eddy current. So it will generate a Lorentz force opposite the direction, which causes a damping effect. Then in the key discussion, he also mentioned did you measure the original damping coefficient, and reported and things that he mentioned in the report. And I believe that it should be calculated because there are friction and air resistance. And so I discussed about the current flow. Will the current flow only be on the surface or the inner part? And the report thinks that it's only on the surface. And in this part, we believe, I agree with the reporter. And here are the points missed, we believe, the opponents and the reporter did. So in the theory part, he missed the calculation of friction and air resistance and how he analyzed it. And also uniformity of the magnetic field, since he used a Helmholtz coil. And Helmholtz coil is actually close to uniform magnetic field. And he didn't mention that also the setup for experiments. He didn't mention the measurements of magnetic field, also the structure of the sphere, like the solid or hollow sphere, also the thickness of the surface, which which the current flow on, and also the releasing method. I believe that there's a more stable way to release a sphere by some machine or other kind of releasing method. And also he missed, both of them missed parameters about conductivity. Also, in the experimental data analysis, they missed the points of angular frequency. And this is the end of my review. Thank you.
2 minutes for author if concluding remark.
Okay, so for the concluding remarks, to respond to the questions of the opponent, we did not consider eddy current. Instead, we thought an approach of Maxwell's first equation. And we spent a lot of time discussing the force and the eddy current. However, I think it's not that necessary and shouldn't be spent so much time on. Also, nanostring was used, and we measured the original damping. Now, to respond to the questions of the reviewer, with a parallel magnetic field, we expect no such phenomenon, that is the extra damping, which is presented in a reference but not shown on the slide. And friction is what causes the damping when there is no extra magnetic field. So the hollow sphere will cause a more significant effect, mainly because its mass is lower, so the rotational inertia is less. So there will be a more significant torque acting on it. Now, eddy current is only on surface, which we both agree on, and the ball is released by hand, whose error is unexpected. However, we agree with the reviewer that by using a machine, we may be able to reduce this error. And thank you.
Any question?
I think it's a good idea to analyze the problem as a damping oscillator and view the magnetic effect as a damping term. Actually, you have shown us the under-damping case. I'd like to see if it's possible to adjust your experimental setup and to investigate the over-damping case.
Can you describe what overdamping case is?
A larger,
Oh, a larger
a
shell.
larger damping term.
Oh, a larger damping. So even the shell just decays without oscillating? Yes, so I think if the shell mass is too large, the shell oscillating motion will be slower, just as we see in the 10-centimeter shell. So I think if the shell is larger, then the damping will be overdamped.
And I believe that the mass of the sphere, also the torsion constant of the wire, will cause the phenomenon of overdamping. If the torsion constant is too big, also the mass of the sphere is too big, which causes a bigger rotational inertia.
I think this is a very interesting point to be discussed. So according to reporters' setup, I think the initial angle that they twist the wire can also cause the underdamping that is main.
The problem statement doesn't restrict this magnetic field to a static field. It can be AC field. So have you considered this or the experiment on this? For example, if this AC field has a frequency close to this torsion.
No, we did not
Torsions,
consider that.
No? You didn't do
We
it.
did not.
Oh, so what do you expect if you have an AC field and the treatment frequency is close to these torsions, pendulums, natural frequency?
I believe that it will affect the damping effect of the sphere, which the reporter didn't mention, but I believe that it's so the sphere will cause with a bigger mass or inducing the magnetic field or.
So, in my opinion, I think in the cases will be the motional in EMF, but in the situations that the professor mentioned will be the induced EMF, since that the magnetic field is time varying. That if you use the AC for the coil.
Sorry, can I adjust my answer? Thank you. So, with the AC, so the eddy current, the direction of eddy currents will be different. So the phenomenon will be not as significant as with using a compost coil, I believe.
Yes, I agree with the reporter because the magnetic field is changing, so there's no particular side for the. Oh yes, reviewer, sorry. So there's no particular side of the torque, so the phenomenon will be less significant.
Reporter, you mentioned that you corrected the angle in the measurement. Can you say again why you corrected it?
I'll correct it because by using a tracker, we cannot enable the overflow option. That is, if our angle is more than 180 degrees, it will register as negative 180 degrees.
Oh, okay, that's what you mean. Okay, fine. And you also mentioned that you have to manually remove some data points.
Yes.
Based on what you did the removal.
Based on what? Based on if the climax point or the peak point is based on if the peak points are too difficult to see by humans.
What do you mean too difficult?
Because there is some non-peak points, and if the non-peak points and the peak points are clustered, then we will not be able to see. Or
Can you show something?
Okay.
Because I don't understand what you mean.
Okay, so let's for example here. Oh yeah, here. Here. So we cannot just we cannot say that where is the
What are these points?
oh these points are due to the lateral motion, because when we release the ball by hand,
What are they?
what are they? They are peak points, but the peaks, what you see here,
Yeah, why it is not like this?
oh, because there is also lateral motion instead of rotational motion.
So you only choose the top point and bottom point to show the next slide?
Yes.
Oh,
Yeah,
okay.
you can see.
I see. Okay.
Okay, thank you. Seven, 8, 8, 6. Hold 8, 7, 8, 8, 7. Reviewer. 7, 7, 7, 8, 7. And
We would like to change problem number 3, 7.
Number 3. Upstairs object.
We accept the challenge.
Please write down your name, ball. So are you ready to go?
Hi everyone, I'm a reporter Hao Zhe from Kaohsiung Senior High School. Today I'm going to report problem number 3, siren. Here's my problem statement. When you direct an airflow through a rotating disc with hole, you may hear the sound. In this video, you can see the experiment demonstration, and the black thing is needle belt, which can produce the airflow. For our main focus, we will have the sound spectrum to analyze your data, including amplitude and frequency. And for my experiment, I will have some relevant parameters, including amount of the host, location of host, rotational speed, and size of the host. Here's my outline. For theory, I will have a simple model to show my concept more clearly. And I will going to discuss 3 things: compression wave, harmonics, and expanding spatial frequency to Fourier cosine series. And for the experiment, I will import the record into Python and conduct FFT figure and to analyze the data by changing this parameter I previously mentioned. And finally, I will have a conclusion and reference. Let's move on to a theory. First, we can see as the left show the air molecules vibrate behind the disk, and it's a reason that's called a compression wave. And then the compression wave can use the Fourier transform to turn time domain into frequency domain. After the background knowledge, we will need to know the definition of harmonic. First, we assume the fundamental frequency will become f, and the harmonic will be multiple relationships. And you can see that in your frequency domain. Then they will have many peaks, and the peaks will be the different harmonics of your sound. And there's a compression wave that you need to know. As the CD rotates, it will be cut into many segments of your air source, and that will cause the air vibrations, which is compression wave, and you can perceive the sound. And there will be our console simulation. We use console multi-physics engine to run some finite element simulation, and there will be the pressure field and velocity field. And this simulation will show the different rotational situation. And you can see as the CD rotates, the air flows will be cut into many segments. That's called the compression wave. And as the CD without rotates, and it will have the steady vortex. For spatial frequency, first we define A of x to be the intersection area of the airflow and the hole. And its waveform can be similar to a series of portions. So after this concept, you can know the frequency is related to rotational speed and the amount of the holes. And amplitude is related to A of x, which means the area coming to the hole and the pipe. So next we are going to make equation derivation. The L means distance between adjacent holes, and x means air source center to hole center, and A means radius of the hole, and the real line circle will be the holes on the CD, and the dotted line circle will be your air source. Then you can know that the black area will be the A of x, which is equal to A of minus x and equal to A of L minus x. Since their period is their fundamental period is 1 over L. And for the Fourier transform, we can write down A of x into Fourier series, and then geometry give this equation. And next, we can get the Fourier component A become this equation. Then we can define z equal to 2 pi NA over L, and we define the S of z function. Then the right corner will show the relationship between S of z function and z value. And there will be the reminder up there. Then we can use the relation below, then compute the n harmonic. There will be the function, and S of function will be the relative intensity, and cosine part will be the natural frequency. And eventually, we can get the fundamental mode, which I mean is the frequency fundamental you can hear is Q times R. Q means amount of holes, and R means the revolution per second. And I will going to discuss the Fourier transform again. then in a complex way, it can be decomposed to multiple single sideways. So through the Fourier transform, you can put the complex way like maybe your siren sounds, and it can be decomposed to multiple sideways. Then I'm going to move on to the experiment part. This will be my experiment setup. For the main siren instrument, it consists of a disc and motor. And for my air source, I will have an air pump and hose, which can make sure that I will have a steady air source. And for the space, I use the acoustic A-foam to make a sound absorbing box to reduce the white noise in your space and some sound reflection, and that will affect your result. And there will be my preliminary work. So for measure the rotational speed, I using sensor and Arduino to measure, and recording I use the direction microphone, which I mean is if you use maybe cell phone or something device to record, you will have a sound distortion that will affect your results. And for drilling, I will have a drill and drilling machine. And below will show my space improvement process from small fan to controllable siren motor, and eventually adding sound absorbing box. And for a program, I will use the Audacity and Python to analyze my data. There will be my schematic on my experiment. The small q means amount of holes, and small r means hole distance, which I mean is a small circle, the holes on the disk and the CD center. And a big R will be the rotational speed, and small a will be the hole diameter. In experiment 1, we change different amounts of holes, which I mean is a small q. I change the 4, 6, 8, 10 holes on it, and fix the other parameters. Then you can see we can get experiment result is 145 Hz, which I mean is the fundamental, and there will be the harmonic behind. And the theoretical model, as I previously mentioned, Ft equal to Qr, we can calculate this prediction will be the 132 Hz, and it is similar to our experiment results. And for a 6-hole situation, we can guess our experiment result will become 205 Hz. And 8-hole situation, the experiment result will be 270 Hz. And 10-hole situation, it will become 325 Hz. And based on this result and some theory I previously mentioned, we can know as the amount of holes increases, the frequency will be higher according to this equation I previously mentioned. And this figure will show the theory comparison between theory and experiment, and it will have the error bar on it. It will be a linear line. For experiment 2, I try to change different location of holes to vary the hole center to the CD center, and fix the other parameters. And you can see that the experiment result, which I mean is fundamental, will become 260 Hz, and our theoretical model prediction will become 264 Hz. And it's really match our experiment and our theory. And this situation will become 3 cm situation, which I mean is the inner circle of your experiment. And for a 4 cm situation, which I mean the holes on the disk and the CD center, and it will become the middle ring, and the experiment result will be 254 Hz. And the outer circle, its experiment result will become 258 Hz. And based on this result, we can know as the host distance increase, it won't affect the frequency. However, it does make the sound louder. And there will be a comparison between our theory and experiments. And for experiment 3, I try to change different rotational speed, which I mean is big R. And I will fix the other parameters. We can see as your rotational speed will become 13 RPS, your experiment result will be 124 Hz. And in 26 RPS situation, your experiment result will become 199 Hz. And at the 33 RPS, your experiment result will become 274 Hz. And at 65 RPS, your experiment result will be 505 Hz. And final, at the 91 RPS, your experiment result will be 704 Hz. And based on these results, we can know as the rotational speed rises, the frequency will be higher. And there's still a comparison between theory and experiment, and they will have the error bar on it. In the final, variable, I try to change different hole diameter, which means the small a. Then you can see the 4 millimeter situation, its experiment result will become 260 Hertz, and in the 5 millimeter, it will become 260 Hertz either. And in the 70 millimeter, its result even is the 260 Hertz. And we can know as the hole diameter gets bigger, it won't affect the frequency. However, it does make the sound louder, and there will be the comparison between the theory and experiment. And finally, I will go into my conclusion. And there will be some key parameter between my theory and the experiment. That's that the frequency is related to n-harmonic amounts of holes, which means small q, and rotational speed. And amplitude is related to n-harmonic amount of holes, small q, location of holes, and hole diameter. And there will be the reminder formula down there. And for the last conclusion, in experiment 1, we can get, we change the different amounts of holes, and you can know as the amount of holes increases, the frequency will be higher. And in experiment 2, we change different location of holes, which I mean is the inner, middle, and outer ring. And we can know as the hole distance rises, the sound will be louder. And in experiment 3, we change different rotational speed, so we can know as rotational speed rises, the frequency will be higher. And in experiment 4, we try to change different hole diameter. We can know as the hole diameter gets bigger, the sound will be louder. And that will be my reference. Thank you for listening.
So first question I would like to ask the reporter. So what is the origin of the sound? Is the pressure wave caused by the disk or the vortex shading? Or both of them happen?
I think the main reason will be, but not the CD vibration. It's the
the pressure wave caused by
yes,
the
compression wave.
Okay.
But yes.
So the vortex shading won't happen or happen?
It will happen, but not the main reason.
Okay, so did you control the wind speed in your experiment?
No, I didn't control the wind speed in my experiment because you can.
So you didn't consider it, right?
Yes, in my situation, I didn't consider it.
Okay, so did you think that the wind speed will change the sound characteristic of the sound, such as the intensity of the sound or the frequency of the sound? If the wind speed increase?
I think that maybe change the frequency, but that it won't affect our.
Okay, thank you. So will the Doppler effect cause deviation in your experiment?
Please.
If the Doppler effect influence in your experiment. Okay, next question. Did you consider the natural frequency of the disk or and the frequency of the disturbance from the wind?
No, I didn't consider it.
Okay, so when we increase the thickness of the disk, will the phenomenon happen significantly or not?
That's not significantly, I believe.
Okay, so when you change the amount of hole, you also change the Z in your theory, right?
Yes.
Okay, so the deviation of relating intensity is come from your what? Can you explain?
Can you speak your question again?
Okay, so the deviation of relating intensity is mainly come from what? It's the disturbance of the wind or the energy deception from the wind cloud hitting on the disk.
I think that's maybe the disturbance of your air source.
Okay, so thank you. Camera judges and flow comparator. And the opponent protein is Celsius, and today what I'm going to oppose is problem number 3, styrene. And here's the problem statement. If you direct an airflow onto a disc with a rotating disc with holes, a sound may be heard. Explain this phenomenon and investigate how the sound characteristics depend on the relevant parameter. And the opponent will focus on what is the origin of the sound and how the different parameters affect the characteristics of the sound, such as the frequency, overall intensity, and the relative intensity. And next is the reporter's outline. First, in the theory part, the frequency will equal to the Hall's number and the angle multiplied by the angular velocity. And he also analyzed the relative intensity of each harmonic by using Fourier series. And for the experiment part, he changed the Hall's number, angular velocity, amount of Hall, and the arrangement of the Hall, which changed the distance between them. And he has no error analysis or the controversy part. And here's the strong and weak point for the reporter. First, he demonstrated the phenomenon which shows the rotating disc with Hall and it generated sound, and explained the Fourier transform. And however, he has an unclear explanation of the overtone frequency which caused by the stationary wave. And he had lack of analysis on the wind speed, because I believe that when the wind speed increases, the total energy from the wind will increase, so the amplitude of the sound will also increase. He failed to illustrate the fundamental frequency and the overtone frequency part, as I mentioned before. And he has no explanation of the vortex shading affect the sound characteristics, since that there has some unexpected peak in their spectrum. And he didn't analyze the experimental error well, such as the disturbance of the wind and the energy deception also caused the intensity error, and lack of explanation of the boundary limit of this experiment. And here's the point to be discussed that I want to discuss to the reporter. First, what's the origin of the sound? I think the main reason that caused the origin of the sound is the longitude wave which is formed by the air particle. And for the fundamental and the overtone frequency, I think it's the free end of the stationary wave might happen. And for the prediction of the characteristics of the sound, first, I want to discuss about what's the relation between the fundamental and overtone frequency, and what's the energy. Wind energy affect the overall intensity, and how the relative intensity of each harmonic affect, things that he has mentioned in the report. And for the parameter part, think how will the angular velocity change will change the phenomenon, and what's the characteristic of the disc, such as amount of hole, diameter of the hole, interval between the holes. And analysis part, use fast Fourier transform, what is the resolution of the fast Fourier transform, and next is about unexpected peak part. Because it has some deviation and unexpected peak, which not belongs to the fundamental frequency and the overtone frequency, which is caused by the longitude wave. And I think it is because the primary vortex 3 happened, which is the vortex shading, and also the Reynolds number of turbulence also caused the experimental error. So I think the measurement of the wind speed difference is important to discuss. And for the microphone part, I think the resonance frequency of the microphone and the position of the microphone is very important, because when the position of the microphone increases, the amplitude will change. And for the resonance frequency of the microphone part, because every device of microphone will has its resonance frequency. So I think the device will cause deviation. So here's my report. I want to give to that part. So, and can you come to the blackboard and okay. So first question I would like to ask is about, you have mentioned what is the origin of the sound, and you say it's the longitude wave, right? Yes, which caused by inflates the side view of the disc.
Yes.
And when the air particle passes through it will be like this. Yes. And however, when our air particle stuck at the front of the hole, it will cause a pressure wave, right?
Yes.
And did you consider that when the rain, since that you didn't consider the wind speed, and when the wind speed increased the...
First, I want to emphasize that in my presentation, I didn't mention that the vortex shading will affect my experiment. And second, in my experiment setup, I will have a sound absorbing box, which I make sure the wind not the main factor in my effect or experiment.
Okay, thank you. The opponent believes that in every situation, when the wind speed is enough, which is including when the vortex shading happened, it was the Reynolds number from 60 to 15,000. So I think it's a large range to happen. So please turn to your page 24.
Sorry, I want to emphasize this concept that in my theory, I try to explain my frequency of the cell will be the rotational speed cuts the air vibration, and it will become in many segments.
Can you turn to page 24? Can you page 24?
You let me explain my.
Okay.
When the CD rotates, the air source will be cut into many segments.
Yes, I get it. I understand this part.
So I think the Reynolds number, that's the main focus. That's the main focus of.
Okay, so can you turn to page 24?
Did you agree?
Yes, I agree in this part. However, I want to 24. Thank you. Then can you explain why is this on the expanded peak limit? Why will it happen?
Can you show more clearly? Can you?
Like this part. What do you think of the like this on the expanded peak? Which is from this?
I think that may be the white noise, and I will have the analysis of this. I have analysis of the light white noise, and the spectrum will be the motor FFT, and we can see that its fundamental frequency will be 60 Hz, and its overtone, or you can see that the harmonic will be the multiple relationship. So I think that the smaller amplitude will become the white noise in my experiment.
Pona believes that the vortex shaping will happen in the Reynolds number 16 to 5,000 range. It's because when the vortex shaping happens, it causes the frequency range that in the 700 to the 900. So it can explain some expanded peak in the reporter's spectrum. And for this part, can you explain why the relative intensity like this?
Sorry, can you explain why your Reynolds number will affect my experiment?
Because the vortex shading only happens in the Reynolds number from 16 to 5,000.
So you think the Reynolds number will affect your frequency?
Well, affect the vortex shading, and the vortex shading will affect the frequency.
So you think the vortex shading will affect the frequency in this situation?
Yes.
But in my concept.
But sorry, it's my time. I want to know why the relation between it's like this.
You need to know in general situation, the fundamental will be the more.
Yes. Can you explain why the second is the lowest and the fourth is largest? Can you explain by your theory?
That will be the S of D function I previously mentioned.
Can you turn to that page?
That page?
The page that shows the SD function.
Okay, I can.
Yeah. The opponent believes that in the reporter theory, the SD function, which means the coefficient of Fourier series, since that the coefficient of Fourier series the meaning is that the amplitude of each wave, and when please turn to this part. So this is which means that the coefficient of Fourier, right? Since that
yes, that's the coefficient of the
Fourier series.
Yes.
So opponent believes that please come to a black hole. So we know that the vortex, the amplitude this coefficient is proportional to this coefficient is we call it as Bn, right? Coefficient in your series A, right?
Yes.
Well, and its square will proportional to the intensity of the cell.
Yes.
Yes. But why in your theory you didn't consider?
In your theory, I didn't consider. You mean what? I didn't consider what?
You didn't consider the amplitude square is proportional to the intensity, since the relative intensity in your situation is not have the square.
So, did you want to simulate my equation derivation process?
No, I just want to see why the result will be like this. Because in the reference.
But that's the conclusion. That's the process of my equation derivation. So that's just the result.
So the opponent believes that it's because the physics explain that the amplitude is always proportional. The amplitude square is always proportional to the intensity. And please turn to
page. Do you know what's the relative intensity?
Relative intensity means that the which harmonic it is.
Yes, so I showed the S502 function, and it can explain why the motor FME will become like this.
And can you turn to page 33?
So did you agree?
Yes, I agree in this part. But however, I want to discuss in the page 33, which shows the intensity of the sound.
36? 33.
Yes, can you explain why there has an error bar in there?
And because in your experiment,
in your
in my experiment, it's not the ideal situation. So you
okay. So do you think that the deviation is come from the energy dissipation from the wind hitting on the disc?
No, I don't.
Because in the reference, it has mentioned that the intensity is the driving intensity, not the harmonic intensity. So the driving intensity of the wind, but if you mean that is an ideal situation, right? I agree with that. But however, when hitting on the disc, it causes the energy deception. So I think this is the main reason that causes the deviation. That is why your experiment is always lower than the theory.
No, but I think if you have the more large energy of your air source, it won't have the more diffusion of your air source, so it won't make the diffusion on there, and the air source will go through the rotational speed, and it can be cut into many segments.
Okay, since that you didn't measure the wind speed in your experiment, right?
Yes, I didn't consider it, and I believe that.
I get it. But how did you make sure that the wind speed is fully passed through the hole?
Because I have the steady air source I previously mentioned.
But however, because the turbulence happens, you cannot know actually situation when the wind speed hitting on the disc. And so, in your experiment, did you only analyze the fundamental frequency, which is n equal to 1?
What can you explain?
Fundamental frequency is that n equal to 1 in your theory.
Yes, n equal to 1. In my fundamental mode, I just you can see the formula I previously mentioned.
Okay. I get it. I understand that part. But did you try to analyze when n equals 2 or n equals to 3?
Yes. In there will show the harmonic behind the fundamental. And
Can you have the graph that shows the relation between the like this the n which is 1, 2?
Yes, I have the graph. I can show you now.
Okay.
And there will be my experiment derivation.
And
there will be the ratio of intensity, and I put it in there.
Can you turn to the previous page? 74 or 73?
74.
Yes, and 73.
73.
Yes. 72. Can you explain why the z is large? The function will be minus the basic function. Can you explain that?
Can you focus on my presentation?
Yes, I focus on your presentation.
That's the math, not the physics.
Oh, I think that if you can derive the solution of it, which will equal to the solution of this function, since that you use numerical solution, which is including Taylor equation, the solution of it will be like this. In my calculation, will equal to this, and this is the Bessel function of it.
No, I think that's not the Bessel function, because the Bessel function is.
It is a strong kind of Bessel function kind.
Yes, it's a Bessel function, like not the Bessel function.
Okay, so however, I believe that this function can predict the phenomena more accurately.
So I think that the opponent have the misunderstanding of all the equation derivation.
Okay, here's my discussion summary. First, we discussed about relative intensity, and the opponent believes that the coefficient of the Fourier series was square most proportional to the intensity, which is the reporter misunderstanding. And we also discussed the origin of the sound, lack of the consideration of it, and as I mentioned before, an expanded peak can also be explained by the vortex shading, which can use Strohholm number to calculate. And the deviation is also come from the disturbance of the air and the energy deception from the wind hitting on the disc. And however, I believe that when the wind speed increases, the total energy will also increase. So the overall intensity will also increase. Like I mentioned in the presentation before. And thank you. Here's my discussion summary.
We are 3 minutes.
So I'm the reviewer, and I want to ask, why does the reporter think that the vibration of the CD is not significant?
Because in my experiment setup, you can, in my experiment setup, I will have a slip on it, and it can set the CD without the vibration, and it can reduce the vibration that the opponent say will affect my results.
Okay, so did you test it? The CD isn't rotating, and the wind blow, with the wind blowing through, will the
No, I think the CD panel wouldn't affect my results. Since my theory says the compression weight is the compression wave frequency is less than Q times R, since the pattern of the disk will not affect my results.
Okay.
So I didn't consider it.
And okay, so do you agree with?
I believe that the vortex shading cannot avoid by the fixed placement of the disk, since that the vortex shading is a very little, is a micro. We can consider in the real situation.
Okay, so
And then I want to emphasize.
oh, sorry. So is the vibration little, like as the opponent's, like that you cannot avoid it?
No, I think that won't affect my results.
Okay.
Yes.
Okay. So did you test that the air blowing, the diameter of the air blowing device is the same as the hole you are conducting?
Yes, that's same.
They are the same, but you will also change the diameter of the hole. Yeah. So you also change the.
No. My meaning is that I set the air source to become bigger than the holes on the disk. So your air source will like this, and the CD holes will be like smaller than the air source.
So it doesn't need to be necessarily as same as the hole you are blowing. So
Yes.
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 And so how do you feel about the?
I think that because when the wind speed increase, the Reynolds number increase, which causes the turbulent situation, so we cannot measure the real airflow situation in their experiment.
So that's the difference of the airflow.
It's why the Reynolds number difference, or because when the Reynolds number is linear flow, it has steady flow. Since that the reporter didn't consider the wind speed in their experiment.
So can you? Oh, okay. problem-free scenario. And so the problem statement is as follows. And the key points are how do the sound happens and how to produce the steady airflow and how do the parameters affect the frequency. This is an overview of my report. And so first of all, the performance and comments of the reporters. And so for phenomenon, they use video demo of experiment and also discuss the sound spectrum. And for the theory, they use AX function, which is good. And also the experiments, the various parameters. And for conclusion, they found that the more hosts and higher rotational speed lead to higher frequency, and while other factors lead to the largest. And for the advantages of the report, they speak loud and clearly, and also they have a detailed explanation of their setup. And for the suggestions, we think that they should put more emphasis on the derivation of AX graph, and also the wind speed should be discussed too. And for the performance and comments of the opponent, his advantage is he adds an abundance of questions in the 2-minute session, and also he has enough volume. However, we found that he avoided theory that is not present in the report. And also, he should discuss more on the experiment, and instead of the mathematics theory part. And he should give the reporter more time to express his opinion. Also, the discussion should be more fun. So for discussion, the opponent asked that if the wind speed controlled, and the reporter said that he didn't consider. And our opinion was that the air speed should be controlled. But maybe you are using the same stripping dock, so it can be so that you should try to control it. And the opponent would ask that will the Doppler effect influence the experiment? And the reporter also said he didn't consider it, with no clear reply. We think that there is no motion of the observer or the source, so maybe the Doppler effects does not play a role in this experiment. And the opponents asked that where does the deviation from the theory main come, and the reporter said that it's from the disturbance of the air source. And we think that the disturbance should be one of the reasons, and maybe the wind can be an influential factor. Okay. So there are also some discussions about the small fluctuations, and the reporter said it could be the white noise, and we also agree. So what I asked was, is the diameter of the air gap at the same radius as the whole air flow? And the reporter said that the CD hole is more than an air gap, and the opponent says that maybe the discussion on Reynolds number is necessary. Okay, so these are these points. Thank you.
Think for the opponent and the reviewer, and I want to remark some points in my presentation. Since that the opponent mentioned many factors that I wouldn't mention in my presentation. So first, I think he didn't focus on my presentation, and next I want to state that I think the wind not the main factor. According to my resource or my setup or my theory. That's because the main reason of the frequency is caused by the air, the CD cuts the air source. So, which I mean is that when you have the one host on each ring, and your rotational speed will become maybe 5 RPS. So your frequency will become 1 times 5, because you have 5 segments. So I think the wind not the factor will affect my result. And they will have some concluding remarks. for a fixed point, I want maybe I should read the reference that opponent reads because I didn't think the Reynolds number of the vortex shedding will affect my result. And discussion repeats. Opponent asked a very question that isn't in our cases, so which we think maybe they could more focus on our presentation. And I think the opponent focused on their reference too much. And first, no discussion about the experiment part such as different effect of the parameters. And for concluding remark, the highlight is that he figured out the reason of the sound produced and using sound absorbing back to avoid the impact of surrounding noise and analyze the different frequency component by FFT and done the experiment to figure out the theory incorrect. And after this discussion, I also appreciate the discussion with the opponent and the reviewer. And thanks a lot.
The problem statement, they talk about controlling parameter to control or determine this sound characteristic. When we talk about sound characteristic, we have amplitude, we have frequency, we have harmonics, and we also have phases between these different components. So obviously, this free transform, you cannot just look at the intensity, but you also have to look at the complex part. So to control such a this fine detail like phases, how do you think you should control the whole pattern on the disk?
I didn't consider the phase because in my experiment I just to import the waveform into the audacity to analyze it. And why I focus on the amplitude and frequency because that's the main factor that influence the waveform. That's caused the different timbre of the sound and maybe different pitch of the sound. So I didn't consider the phase in my presentation.
Can you explain why the phase in your fraction? Sorry.
Different harmonics, it doesn't. There will be some phases difference.
I believe that in our English problem statement, we should focus on the frequency, overall intensity, which caused by the wind speed increase, and the relative intensity, which caused by the SD function in the reporter's report, and also the vortex shading also caused some unexpected take in their experiment. So I think there is all the origin of the sound and the characteristics of the sound that should investigate in this problem.
Sorry, I want to add in some words that I think the professor question would be the great opinion, but it didn't consider my experiment. So I think in the future I will do this for my experiment to make the presentation more in text.
Page
4.
24.
24.
You mentioned the bigger size of the hole will produce a louder sound. I would like to see what you mean by louder, whether it is the Fourier spectrum, the background noise in your Fourier spectrum, louder the noise, the larger background.
It means the amplitude of the four.
I don't know what you mean by louder.
The louder is
whether you can show in the Fourier spectrum.
Because
here,
if you have a more larger intensity, you have a larger amplitude. So in the y-axis, you can see that this amplitude has the more large intensity, and which I define as the fundamental mode, and it's my experiment result 135.
So you mean a louder is a bigger amplitude, not the noise, a larger noise.
Yes, yes.
I think that when we change the radius of the hole, it changes the amplitude of the sound. But it cannot explain all the unexpected take in the report, reported report. Yes.
So maybe you can look at the original data and compare it with the intensity values and find the local maximum.